Good morning, guys. Today what we're going to do is work on estimating a population proportion using confidence intervals. So we're going to take that general idea of how to build any confidence interval and focus specifically on proportions today. So let's look at our setup. Our principal claims that only 10% of students went to the basketball game the other night. We were skeptical, so we asked a random sample of 75 students if they were at the game. 15 said they were. Does this study provide us with sufficient evidence to reject the principal's claim at a 90% confidence level? He says 10% went. We got a random sample with 15 of 75 going, which is about 20%. So we want to know, does that one sample give us enough evidence to say that, no, he's probably incorrect? And we're going to test this using 90% confidence level. Now, before we do any type of inference where we're trying to draw conclusions about a population based on a sample, we've got to make sure that that sample was well designed, was carefully selected. So we do that by checking the conditions of our study. So the three conditions we are always going to check is randomness, independence, and an approximately normal sampling distribution, so normality. Sometimes we don't hit on this, so we have to make adjustments and go to a different type of sampling distribution. We're always going to check for it initially. So randomness, there are two different ways that we can get randomness. We can either have a random sample, or we can do a randomized experiment where we randomly assign treatments. But we have to have some form of randomness in the study. So in our study, did we have randomness? Well, we know it's observational. Did you go to the ball game? Not assigning people if you go to the ball game. So we miss on the random assignment, but we do hit on the random sample. We can see it right here. Random sample of 75 students. So we would cite that evidence. Random sample of 75 students. So yeah, we met the randomness condition. We're just going to write it down. Just going to pull out of the study, the description there, where we see randomness. Independence. Again, we've talked about all of these. We're going to go a little more in depth to make sure we're getting in the habit of every single time we do a problem, it's going to use these. So independence, two different ways we can get independence. One, is it reasonable that the individuals are independent? So one person's response would be independent of another, or one object's measure is independent of what another object measures. So that's what we mean when we say independent. So we can either just have kind of common sense independence, or we can have a more ordered way of checking for independence, and that's through our 10% condition. This is what we're going to use, or what we're always going to kind of look for. This is what we fall back on a lot of times if for some reason we failed 10% condition. So 10% condition, are the samples small enough that we can say, yeah, the people it should be spread out far enough in opinions that we could reasonably assume that they are independent in their responses. So sample size just needs to be less than 10% of the population. Well, did we meet 10% condition in this case? Well, our sample size was 75. We got about 2,100 kids in the school. So there it is. That's all you have to do. You just say 75 students is less than or equal to 10% of all RHS students. So I don't have to actually calculate the 10% of our 2,100. Like we just know it's kind of an intuitive thing. 75 is less than 10% of the school. All right, so we've met independence condition. Now let's check for that normality condition, or normality of the sampling distribution. So the way we do that with proportions, we looked at proportions, we've looked at means. With proportions, remember, it's large counts conditions. Okay? Proportions are always going to be a large counts condition situation. Means, we look for large sample, that central limit theorem idea. But large counts condition is what we're going to go with here. If we failed large counts condition, we would find some other strategy to be able to do these approximations. Probably just falling back on on binomial distributions or something like that. But we're gonna try to design our studies right now to meet this large counts condition. So, and the condition hasn't changed. It's the same one we've been working with. N times P is greater than or equal to 10. N times 1 minus P is greater than or equal to 10. So sample size times probability of success is greater than or equal to 10. So we expect at least 10 successes or 10 guesses. And then N times 1 minus P. N times 1 minus the success gives us our total failure. So Sample size times probability of failure also needs to be greater than or equal to 10. So that means that we expect at least 10 no's. So at least 10 yeses and at least 10 no's. It's not one or the other. It's got to meet in both groups. Now we kind of have two different things going on here. We have the expected yeses. So he says 10% of the school. So we expect 10% of the school to be a yes, and we would expect 90% of the school to be a no. Other than so our sample, we would think should mirror that. But sometimes we don't know that. Sometimes we don't have a claim to test against, and we're doing a study for the first time, and we're trying to be the ones that set this initial estimate. So in those situations, we don't go off what we were told the probability of success is. We're going to go off of what we actually observed. So we would want to observe at least 10 yeses and at least 10 no's. So maybe you're sampling and you keep sampling and you're getting like 3, 4, 5 yeses, and the no's just keep piling up. No, 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 no. Maybe I've got 50 no's and still only 2, 3, 4, 5. In that situation, you just keep sampling, no matter how high those no's get. Keep sampling until those yeses have got up to at least 10 individuals saying yes. That's what we're talking about. So it can be the expected if we know what's going, or have a good idea of what's going on in the population, or it can be the observed. Now, since I'm pretty sure our principal just pulled this 10% out of thin air, we're not going to say that that was a well-designed estimate of what's going on in the population. I think he was just throwing off a comment. So we're going to use what we've observed. So can be expected or observed. So we observed 15 students attending. So that's greater than or equal to 10. And we observed 60 students. Right, that's the rest of the 75. Not attending. That's also greater than or equal to 10. So we're just throwing our evidence out there. Do we feel like this was a large enough sample? And we're going to say, yeah, because when we sampled, we got at least 10 people who did go to the game and at least 10 people who said they didn't go to the game. All right, so those are the conditions we always need to be able to meet when we're working through. Now, sometimes you don't meet every condition and then adjustments have to be made, but for what we're doing, we should be meeting these conditions right now. The failing to meet conditions is kind of the more advanced courses in statistics. So now that we've met conditions, let's get in and actually calculate the confidence interval based on our sample. So to kind of recap what we did with confidence intervals on the last one, the generic setup of any confidence interval is a point estimate plus or minus a critical value. Remember, critical value is tied to your confidence level times standard deviation of the statistic, the variability of the sampling distribution. Now remember, point estimate plus these two things, these together make up your margin of error. Critical value plus standard deviation of statistic. Now we're focused on proportions today. So if we have the point estimate of a proportion, that's just p hat. We use all of our possible sample proportions to estimate what's going to happen in the actual population. Now we're going to kind of give a name to this now. So this is now critical Z. So the critical value, or Z with an asterisk, critical Z, is just the Z-score that corresponds to the confidence level that we're interested in. So we were interested in a 90% confidence level. So let's see if we can figure out kind of how we would figure out what that Z-score is. So what do we mean by the Z-score corresponds to confidence level? Well, we know that we met our normal condition. So this is kind of why we're working with Z-scores. So under the normal condition, we know that the normal, or the sampling distribution of sample proportions looks approximately normal. So there's a confidence level associated with that. That confidence level would have the area that takes up the middle portion of the graph. So remember, we want a confidence level that is wide enough to cover a certain percentage of all possible samples. If this is all possible samples represented in that graph, we need a confidence level that covers, in this case, 90% of all possible samples, so a wide interval. So we want to find the Z-scores that would kind of box in that confidence level. So those would be negative critical Z and positive critical Z. Well, if we want to actually estimate what that value is, we're going to have to get into our calculator a little bit. So the way we would do that is using inverse norm. Remember, that's how we find confidence level. Okay? That's how we calculate a z-score. If I need an area, I use normal CDF. If I need a value that marks off a certain area, then I'm going to use inverse norm. So we're going to use inverse norm, the inverse norm feature of our calculator. And we remember that inverse norm asks three things from us. It asks for the area. Remember, that's the left side area. It asks us for mu, and it asks us for sigma. Well, mu and sigma are easy. We know what mu and sigma, if you're dealing with z-scores, if you're dealing with your standard normal curve, mean is always 0, standard deviation is always 1. It's the area that's going to be the interesting part. Well, the area to the left side, two ways I could do it. I could, one, figure out this little area, or two, I could figure out this bigger area. And depending on which area I use is going to give me which z-score. It's mirror image, right? So it's a symmetric distribution, so I just always work with the one on the left side. It's easier to find. So I need to figure out what this area right in here is. That's what I'm going to put, whatever that number is, that's what I'm going to put in for left side area. Well, we have a way we can calculate every single time without even having to draw this graph out. So let's think about what we have. Confidence level is this middle portion of the graph. It's within so many standard deviations of the mean, which is 0. So that means all the stuff here on the outside will be the leftovers after if we've got rid of our confidence level. So it's just 1 minus your confidence level. So the middle portion is our confidence level. What's in the tails is 1 minus the confidence level. Well, I don't need both tails, I just need one tail. So that means that this area is just 1 minus confidence level divided by 2. It's half of that leftover area. That'll be your area every single time when you're trying to estimate a critical value. So it's 1 minus confidence level divided by 2. That just says CL for confidence level. 1 minus confidence level divided by 2. So say I had an 80% confidence level, 1 minus 0.80 divided by 2 is 0.10. Say I had a 70% confidence level, 1 minus 0.70 divided by 2 is 0.15. Say that I had a 95% confidence level, 1 minus 0.95 is 0.025. So I know what this area is every single time without having to draw this out. It's always going to come off of the confidence level we're looking for or wanting to work with. It's 1 minus confidence level divided by 2. So with that in mind, we should be able to calculate what that is. So we know we're estimating with p hat. We know we're going to build our margin of error starting with our critical score, which comes off of this inverse norm function. Then we get into standard deviation of the statistic. Now, standard deviation of the statistic, in this case, is standard deviation of p hat. What's the spread of this sampling distribution? Not the standard norm, but the sampling distribution for this population. Now, we know that's based off of square root of p times 1 minus p over n. We have a problem. If the study's never been done, if we're looking at a population for the first time, we don't know what the population proportion is. Most times when we're doing a study, we don't know what's going on in the population. That's why we're doing the study. So it's really hard to use standard deviation. So what happens in those cases, if we don't know p, which is the population proportion, then we have to use the next best estimate we have, and that's our sample proportion. So we know we did a random sample. We have a representative value of the population in this p hat, or what we hope to be representative. So we're going to have to use that as our best guess of what's going on in the population. So instead of dealing with standard deviation of p hat, of sample proportion, we're going to be now dealing with the standard error of p hat. So you'll sometimes see that abbreviated SE. So just like sigma tells us we have population information that we can plug in, SE, or standard error, tells us that we're going to have to use sample information to plug in. So instead of square root of p times 1 minus p over n, it's square root of p hat times 1 minus p hat over n. Now I know you're thinking, oh goody, another standard deviation formula to remember. But really, if you'll just keep in mind, the difference between standard deviation and standard error is we're just changing out population numbers for sample numbers. That's it. The format of it is going to be the same. So this is the standard deviation that we're going to use, because that 10%, we can't trust that as an actual good estimate of the population, because Again, I think he just pulled that number out of the air. So we now know how we can calculate our confidence interval. We have our sample proportion, our point estimate, and then we can get a critical value and we can get the variability of that statistic. So let's go in and actually calculate this out. So I have a confidence interval of 90% that I'm looking for. My sample proportion, so what did we actually see in our sample? Well, we had 15 students who said yes out of 75. So 15 out of 75 went to the ballgame. I can get this value right here by just using the calculator. So when I go over to my calculator, and we go inverse norm on the calculator, area, I'm actually going to type in 1 minus 0.90 divided by 2. 1 minus 0.90 all over 2. I'll show you on my calculator right here. So we just pick up our calculator, and in the inverse norm function, we're going to type 1 minus 0.90 over 2. I don't have to do any of that arithmetic in my head. I just type it right in, put in the mean, put in the standard deviation, and then we're going to hit enter. Down there on paste, and you can see that the estimate is at negative 1.64. So a z-score of 1.64, why am I making it positive if it's negative? I got the plus or minus. It doesn't make a difference. It's going to be both positive and negative anyway. So z-score is going to be 1.64. I'm going to give you a piece of advice right now. Go ahead and memorize that, because that's the same every single time. All 90% confidence critical z's are always 1.64, because this information has nothing to do with the study. There's no sample data in here. There's no sample size. There's no sample proportions. There's no sample means. This is based purely off of your confidence level. So anytime you're wanting to deal with a confidence level for something that's a normal distribution, 100% of the time, 1.64 is what you can use. And we're going to get in, we're going to work with some 95% confidence levels, and you're going to see that that's 1.96 every single time. So you'll get to where this right here on common ones like 99%, 95%, 90%, 80%, ones we use again and again and again, you don't even have to do this because you're just going to have those 4 or 5 common critical values memorized out. And when we get into our other types of sampling distributions like chi-square distributions or t-distributions, they'll have certain values, critical values associated with them, and hopefully you get familiar enough where you're not having to throw that in the calculator. You just remember this distribution has this critical value because we have used the same ones again and again. So we can get our sample proportion, we can get our critical value, and we can get our standard error. So if we calculate standard error, square root of p hat, well, that's just 15 out of 75 times 1 minus p hat. So 15 people said yes, there were 60 who said no. All over 75 total people. So that's the calculation. That's getting it set up. At this point, it's just throwing it in the calculator. So when I do the arithmetic on this, we get 0.2 people, so 20% of our sample went to the game, plus 1.64 was our critical value, times the 0.046, or 0.46. From there, we just keep calculating, and we end up getting a confidence interval of 90%. That's 0.02 plus or minus 0.076. So you'll see your confidence intervals written like that a whole lot of time. 20% plus or minus the margin of error 7.6%. So our sample came out 20%, but we know that reasonably it could have been 7.5% smaller or 7.5% bigger. So sometimes you'll also see it actually written out in interval notation. So if I did 20% plus the 7.6%, I get 0.276. Or if I did the 20% minus the 7.6%, I'd get 0.124. So this is the other way that you will see confidence intervals written in interval notation. All right, so just if we recap what a confidence interval is, what we talked about the last one, if I was to interpret what this means, what this 0.124 to 0.276 is, that's just saying that we are 90% confident that the true proportion of RHS students who attended the game is between 0.124 and 0.276. We talk in terms of percentages, we're 90% confident that somewhere between 12.5% and 27.5% of students actually went to the game. All right, so with that in mind, that we're so confident that the true proportion is somewhere between those two numbers, I want you to pause it right here and see if you can write a really good conclusion for how we can respond to the principal's statement. Hopefully your conclusion looks something like this. Yes. So as I came up with, since the principal's claim of 10% is below our entire confidence interval of 0.124 to 0.276, we have sufficient evidence that he is probably wrong, probably incorrect with his assertion. Therefore, we can say that the true proportion of students who attended the game is greater than 10%. We're 90% confident somewhere between 12.5 and 27.6. So his claim was not between those numbers, so he probably is not correct. That's what we're trying to say here. So this is a good formal way of explaining that. So that's kind of how I want you guys to go about phrasing your conclusion or interpretation of a claim against a confidence interval. All right, now I want to get into this idea of that confidence interval, because if we look at this one, 0.124 to 0.276, it's a pretty big interval. It's a big net. So and to me, there's a big difference between 12% and 28%. One of them's close to a 1 out of every 9 times, and the other one's close to 1 out of every 4 times. So big difference there in those two values. So let's see if we can get into and maybe manipulate this confidence interval, or at least the margin of error, a little bit more.